Welcome back to G Fun Facts Online. Today, we are looking outward. We are looking at the rusted dust and frozen potential of the red planet. Mars has taunted humanity for decades. It sits tantalizingly close on a cosmic scale, yet it remains frustratingly far in human terms. When we talk about going to Mars today, the conversation usually revolves around big rockets, the Space Launch System, or Starship. These are incredible machines, but they rely on chemical propulsion, the same fire and smoke technology that powered the V2 and the Saturn V. And that is a problem. With chemical rockets, a round-trip mission to Mars is a multi-year commitment. It is a logistical nightmare that exposes astronauts to dangerous doses of cosmic radiation and the intense psychological torment of isolation. But there is an alternative. It is a technology born in the atomic age, tested in the deserts of Nevada in the 1960s, and it fundamentally changes the math of deep space flight. It promises to cut travel time in half and offer safety options that currently do not exist. This technology is nuclear thermal propulsion, or NTP. To understand why we need to put a nuclear reactor inside a rocket, we first have to respect the tyranny of the rocket equation. Rocket science is ruled by the Tsiolkovsky rocket equation. It dictates that the change in velocity a spacecraft can achieve is strictly a function of its exhaust velocity and the ratio of its initial mass to its final mass. In a standard chemical rocket, energy is released by breaking chemical bonds. You mix a fuel, like hydrogen or methane, with an oxidizer, usually oxygen. You burn them, and you blast the resulting hot gas out of a nozzle. The efficiency of this process is measured by something called specific impulse, or ISP. Think of ISP as the miles per gallon of space travel. It represents the seconds a pound of propellant can deliver a pound of thrust. The very best chemical engines, like the main engines on the space shuttle, max out at an ISP of around 450 seconds. This is a hard limit imposed by chemistry. You physically cannot get much more energy out of breaking those molecular bonds. To go faster with chemical rockets, you need exponentially more fuel, which adds mass, which requires more fuel to lift, leading to a point of diminishing returns. You end up building massive rockets just to lift the fuel for the rocket. Nuclear thermal propulsion cheats this limit. Instead of burning fuel, an NTP engine uses a small fission reactor to heat a propellant, typically liquid hydrogen, to extreme temperatures. This is the key difference. There is no combustion. And because there is no combustion, we don't need an oxidizer. We don't need heavy oxygen, which weighs 16 times more than hydrogen. The exhaust from a nuclear rocket consists of ultralight hydrogen atoms moving at incredible speeds. The result is a specific impulse of 900 seconds or more. In plain English, a nuclear rocket is twice as efficient as the best chemical rocket physically possible. For a Mars mission, this efficiency doesn't just mean saving fuel. It means speed. It means brute force. Let's open up the engine and look at the hardware, because this is not the nuclear power source you might be familiar with. When people hear nuclear in space, they often think of the RTGs, the radioisotope thermoelectric generators used on rovers like Perseverance. Those use the passive heat of decaying plutonium to generate a tiny trickle of electricity. An NTP engine is a completely different beast. It is a high-power density flying reactor designed to run at thousands of degrees. At the core of this system are the fuel elements. Modern designs, such as those explored in the recent DRACO program, utilize something called HALEU, high-assay low-enriched uranium. Unlike the weapons-grade uranium used in the early Cold War designs, HALEU is enriched to between 5 and 20% U-235. It strikes a crucial balance. It is potent enough to generate the required neutron flux for a compact core, but it is significantly harder to weaponize, which eases a lot of the proliferation concerns involved in launching nuclear material. The fuel itself has to survive hellish conditions. Engineers use Cermets, a ceramic metallic composite. The ceramic part is usually uranium dioxide or uranium nitride, which actually holds the fissile material. The metal matrix is made of tungsten or molybdenum. This metal skeleton holds the ceramic fuel in place and provides structural integrity even when the core heats up to 2700 Kelvin. That is 400 degrees Fahrenheit. Recent advancements have moved away from the graphite composite fuels of the 1960s, which were prone to cracking and erosion under the flow of hot hydrogen. These modern Cermets are tough. They are built to withstand the brutal environment inside the engine. To keep this reaction going, we need a moderator. When uranium atoms split, they release fast neutrons. To sustain a chain reaction with HALEU, those neutrons need to be slowed down. Modern designs often employ zirconium hydride as a moderator. It is incredibly efficient at slowing neutrons within a small volume, allowing the reactor to remain compact. This is critical for a spacecraft where every single kilogram matters. And finally, there is the coolant. In a terrestrial nuclear plant, water cools the reactor and spins a turbine. In an NTP engine, the liquid hydrogen is the coolant. It flows through tiny channels in those white-hot fuel elements, picking up heat and transforming from a cryogenic liquid at negative 253 degrees Celsius to a superheated gas in milliseconds. This gas expands explosively through the nozzle, and that is your thrust. So what does this hardware actually buy us? The primary selling point is time. A conventional mission to Mars, known as a conjunction-class mission, follows a minimum energy Hohmann transfer orbit. You launch when Earth and Mars are aligned. You coast for 7 to 9 months. You stay on Mars for over a year waiting for the planets to realign, and then you fly 9 months back. The total mission time is nearly 3 years. NTP enables what we call opposition-class missions. With the high efficiency of nuclear propulsion, a spacecraft doesn't have to coast. It can burn its engines longer and harder, taking a direct, high-energy trajectory that cuts across the solar system. This reduces the one-way transit time to between 100 and 120 days. A round trip could be completed in under a year, or allow for a short stay of 30 to 60 days on the surface before returning. This is colloquially called the 100-day dash. But speed isn't just about impatience. It's about survival. The most critical safety feature NTP offers is the ability to turn around. In a chemical rocket, once you perform the Trans-Mars injection burn, you are committed. You are on a roller coaster that doesn't stop until Mars. If a life support system fails halfway there, or a crew member has a medical emergency, there is nothing you can do. You do not have the fuel to turn back. With NTP, the massive delta-V capability allows for abort modes. Even weeks into the flight, the ship could perform a high-energy burn to loop back to Earth. This capability to abort simply does not exist with chemical rockets, and it fundamentally changes the risk profile of human deep space exploration. Now, we have to address the elephant in the room: safety. The phrase nuclear rocket instinctively triggers alarm. People worry about explosions on the launch pad or radioactive re-entry. But engineers have spent decades designing protocols to mitigate these risks. The first line of defense is the cold launch. The reactor is launched cold and inactive. The fuel is not highly radioactive at launch because the fission process hasn't started yet. If the rocket blows up on the pad, the uranium fuel elements would scatter, presenting a toxic heavy metal hazard similar to lead, but not a radiological one. There is no Chernobyl cloud from a cold reactor. Furthermore, during launch, the core is fitted with poison wires. These are neutron-absorbing rods inserted into the reactor core that physically prevent a chain reaction from starting. Even if the reactor were crushed or submerged in water, which usually acts as a moderator and increases reactivity, these wires ensure the reactor stays dead. They are only withdrawn once the spacecraft is safely in space. And that leads to the third safety protocol: nuclear safe orbit. The nuclear engine is never fired in the lower atmosphere. a conventional chemical rocket lifts the NTP upper stage to an orbit typically above 1,000 kilometers. At this altitude, the orbit is stable for hundreds of years. If the engine fails to ignite, the reactor will not re-enter the atmosphere for centuries, giving the radioactive elements time to decay, or giving future generations time to retrieve it. So where does this technology stand today? For the last few years, the torch for NTP was carried by the DRACO program, the demonstration rocket for Agile Cislunar Operations, a collaboration between DARPA and NASA. The goal was to fly a demonstrator by 2027. However, in July 2025, news broke that the DRACO program was being canceled due to budget constraints and shifting strategic priorities. This is a heavy blow. But while this specific flight test may be grounded, the engineering reality remains unchanged. The physics of nuclear thermal propulsion is sound. The fuel designs, specifically the HALEU Cermets, have been matured. The mission architectures for Mars demand it. The cancellation of a specific program is a setback, but the technology itself is inevitable if we are serious about becoming a multi-planetary species. Chemical rockets are like the galleons that hug the coast. They are perfect for getting us to the moon. But to cross the ocean to Mars and beyond, we need the steamship. We need the nuclear engine. Nuclear thermal propulsion represents the threshold between being a species that visits space and a species that masters it. It replaces the delicate, months-long drift of chemical rocketry with the brute force of atomic energy. It offers speed, safety through abort capability, and a power density that chemical reactions simply cannot match. The engineering is difficult. The politics are complex, but the math is undeniable. If we want to see humans walk on the red planet in our lifetimes, and more importantly, see them return safely home, we must embrace the power of the atom. The road to Mars is paved with uranium. Thanks for listening to this deep dive on Fun Facts Online.